Hello, everyone. Welcome to the Cambridge University Astronomical Society's weekly talk. I'm Xavier, the chairperson of the society. So tonight we have Dr. Jost Migenda with us to give a talk titled Watching Stars Explode, Observing Supernovae Neutrinos with Hyper-Kamiokande and SNEWS 2.0. Before we begin, allow me to share a little more about our speaker. Dr. Jost Migenda is a research associate in the experimental particle and astroparticle physics group at King's College London. After graduating from TU Munich with MSc in nuclear, particle, and astrophysics, they joined University of Sheffield as a PhD student to investigate Hyper-Kamiokande's ability to distinguish between different computer simulations of supernovae. At King's, they work on astrophysics and DAQ development for Hyper-Kamiokande and Super-Kamiokande. They are also a member of SNEWS 2.0, which uses neutrino detectors around the world to provide an early warning to astronomers when the next galactic supernova is coming. Now, without further ado, Dr. Jost, please.
Thank you very much. And almost done with the setup. This is the pointer. Okay. We really should have done this before the talk. I think that's. This is working. This is working. Excellent. So thank you very much for inviting me. Thanks everyone for attending or for watching the live stream. I think already covered most of this. So today I will be, first of all, giving an introduction, talking about what is neutrino astronomy anyway. Then I'll talk about the detector I'm working on called Hyper-Kamiokande, and give you a bit of behind-the-scenes glimpse at what it's like to build such a huge detector. I'll talk about supernova neutrinos and what we will learn from them with Hyper-K. And at the end, I will talk about the SuperNova Early Warning System, or SNEWS. Now, I realized just, I think 3 weeks ago, he had this other talk by Patrick Dunn on neutrino physics, where he gave this excellent introduction to neutrinos, how we, why we think that those particles might exist, how we detected them for the first time, and a lot of, good overview of neutrino physics. So I will skip all that. I think the talk is online, so you can watch the recording, and I'd highly encourage you to do so. For the purposes of my talk today, all you need to know about neutrinos is that they are kind of like ghosts. So what I mean by that is they can quite literally go through walls or through other matter like your body. So in fact, we can do a little experiment right here and now to try and figure out how often neutrinos interact. And I'll need to do a little setup for this experiment. But I will need your help. So please take a deep breath and prepare. Okay. Okay, are you all ready? Yeah? Okay. So what I need you to do for this experiment is to please give me a thumbs up. Excellent. So there's two things happening right now. First of all, you're giving me a massive confidence boost, which I really appreciate because I'm not used to talking for real people anymore. But more importantly, somewhere in that direction out there, the sun is shining just below the horizon. And it's producing a lot of neutrinos in addition to heat and light. And these neutrinos are flying to Earth through the wall of this building and then through your thumbnail. And right now, as you're listening to me, about 60 billion neutrinos are flying through your thumbnail every second. How many of them do you feel? How many? None. See, so that's how ghost-like neutrinos are. So they really just go straight through all normal matter without leaving a trace, without interacting. And after neutrinos were originally proposed by Wolfgang Pauli in 1930 to save conservation of energy in some nuclear processes, a few theorists, a few other physicists, notably Enrico Fermi, developed a theory describing the neutrinos, figured out roughly how often they interact. And the result was, quote from a 1934 paper, that there is no practically possible way of observing the neutrino. So we decided to just give up, do something else. End of the talk, thank you. No, of course not. We still kept on searching for it, and it took over 20 years until 1956, but we finally detected them. And before we go on, I just want to take a moment to note that these two people here who wrote this paper, as well as two other physicists who are really important in the early history of neutrino physics. Wolfgang Pauli, who originally came up with the idea that this new particle might exist, and Enrico Fermi, the Italian theorist who developed the first description of neutrinos, and who also popularized the name. These four all have one thing in common. Well, two things. First of all, they're all white men, because physics back then had an even worse diversity problem than it does today. But more importantly, they're all refugees. They all lived in Central Europe in the 1930s. And then when the Nazis came to power in Germany and the fascists in Italy, they had to leave their home country and move to the UK or the US. And I just want to mention this because it's really important to remember that science sometimes happens in a physical vacuum, but never in a societal one, never in a historical vacuum. So I think that's really important to remember. And even in times like these, where we have some, we have Trump or some Trumpist people elsewhere, where we have a Black Lives Matter movement, where we have many different struggles. It's important to note that those are not separate from science, that these all affect scientists, and we as scientists should be afraid to speak up. Okay, back to neutrinos. So neutrinos are like ghosts. And that, in a way, makes them great for astronomy, because these neutrinos can escape from places where no other particles, no other messengers can escape from. So we can use them to study, for example, the interior of stars. So that makes them great for astronomy. On the other hand, neutrinos are also terrible for astronomy, right? Because they're incredibly hard to detect. You build a detector, most of them, like with your thumbnail, will just go straight through without leaving a trace. Incredibly hard to detect. And also because we don't detect the neutrinos themselves, we wait for the neutrinos to interact, and then we detect the interaction products. That gives us pretty poor angular resolution. So what you see here is the best photo of the sun ever taken with neutrinos by the Super-Kamiokande experiment in Japan. This is about 4,500 days of data taking. And you can see it's pretty blurry, pretty pixelated. So neutrinos are terrible to do astronomy with, but we still have no other way to learn about things like the interior of stars. And that brings us to one more big difference between astronomy, electromagnetic astronomy with light, and neutrino astronomy. And that is while you build these these electromagnetic telescopes, typically on top of a mountain, so you don't have as much interference from the atmosphere, you don't have light pollutions from cities down below, where you can build your neutrino detectors in principle anywhere. Where you usually want to build them is deep underground, inside a mountain. And that's because, you know, neutrinos don't care. Neutrinos will just go straight through that mountain without being stopped. But all the other particles that are raining down from the atmosphere, all these cosmic rays, they will give you a big problem with lots of background events if you build your detector on the surface. So having this huge stack of rock on top of your neutrino detector helps stop those cosmic rays. So only the neutrinos can get through. Okay, so that's a brief introduction to neutrino astronomy. Next, let's talk about our detector, Hyper-Kamiokande. And this is really the third generation neutrino detector in this family. It all started in the 1980s with the original Kamiokande detector, named after the town of Kamioka in Japan, which is quite near where it's built. And Kamiokande was originally built for something completely different, to look for proton decay. Didn't find it, but shortly after building this, they had an idea of how they could upgrade the detector just a little to be able to detect neutrinos from, for example, the sun or from a supernova. So they did some refurbishments, turned it back on in early 1987. Just a couple of weeks later, February 23rd, 1987, they observed this. Pretty normal star over there suddenly exploded in what's called a supernova. And they observed neutrinos from this event, which earned the leader of the experiment, Koshiba Sensei, the 2002 Nobel Prize for basically starting this field of neutrino astronomy. So it was incredibly successful. And yet, you know, they were hitting the limit of what they could do with a detector that size. So they built an even bigger one, and they very creatively called it Super-Kamiokande. Super-Kamiokande was built from the start to look not just for proton decay, which we still haven't found, but also for neutrinos, and in particular for a phenomenon called neutrino oscillations, where you have these three types of neutrino. One of them produces electrons when it interacts. One of them produces a heavier sibling of the electron called a muon when it interacts. And these can turn back and forth into one another as they travel. And I think the talk 3 weeks ago had a little more about neutrino oscillations. So this was a pretty mind-blowing discovery, right? It's like when you're throwing a basketball, and then when you catch it, it suddenly arrives as a football. It's weird. It's really weird. So for the discovery of neutrino oscillations, Super-Kamiokande and its leader Kajita-san got the 2015 Nobel Prize. And today, Super-Kamiokande is still running, but we are once again hitting the limits of what we can do with a detector of that size. So we're building a new, even bigger one. And once again, we're very creative, and we're calling it Hyper-Kamiokande. By the way, if any of you are into languages, super and hyper mean exactly the same thing. Just one is Latin, one is Greek. And I guess Greek is obviously better than Latin. Details of the Nobel Prize yet to be determined. So we've got these detectors, and in Super-Kamiokande every day, I said you've got 60 billion neutrinos going through your thumbnail every second. So Super-Kamiokande, of course, is a bit bigger than your thumbnail. It's like 40 meters tall, 40 meters in diameter. So you've got about 10,000 billion neutrinos going through there every day from the sun. And we detect about 10 or 15 of them. So let's look at what one of these detections could look like. So here we are inside Super-Kamiokande. It's filled with water. That's why it's all blue. And then in here you have a single electron I'm highlighting. And then you've got neutrinos going through the detector. Not just one, not just a few, but a lot of them. And most of them go straight through without leaving a trace. But every once in a while we're lucky. And 10 or 15 times a day, one of these neutrinos will come along, will actually hit the electron and give it a little kick, like billiard balls. And with this little kick, it will give the electron so much energy that the electron, and bear with me here, this may sound weird, the electron will actually move faster than light in water. Still slower than light in vacuum, which is the absolute cosmic speed limit. But in water, light moves a bit slower, so the electron can be faster than light in water. And what happens then is it emits chunk of light to slow down. And if you've seen pictures of a nuclear reactor, where you've got this kind of bluish glow in the water, that's exactly the same thing. And what this Cherenkov effect is kind of like a, like a sonic boom, but with light instead of sound. So you've got this flash of light sent out in a cone, and then it hits the walls of the detector. And this is inside Super-Kamiokande. When we opened it for maintenance, you can see here, there's a human on a boat in the tank doing some repair work. So you can see a bit of the scale of this. And then all over the inside walls, we have these kind of golden spheres, and these are photodetectors. That's what one of them looks like, and they detect the Cherenkov light. That's one of them next to me for scale. So they're about 50 centimeters in diameter. And then this cone of light, when it hits the wall, you get this little ring of photosensors that get hit. And from that, we can determine the energy of the particle by how bright it was, how much light it produced. And we can determine the position of the interaction as well as the direction. So that's, in a nutshell, how our detector works. And now, in addition to this inner detector here, I was just showing you, we also have a small, 1 to 2 meter wide outer layer called the outer detector. And this acts as kind of a shielding. So if there's any radioactive elements in the surrounding rock, so those can't get into the inner detector where we're looking for neutrinos, as well as sometimes if some muons from cosmic rays have enough energy that they don't get stuck in the rock, but they actually make it all the way through to our detector. And then with this outer detector, we can see, there's something coming in from the outside, going through our detector and then exiting, and we can safely throw that away because we know there was something else. We don't want that because neutrinos, of course, don't leave a trace in the outer detector when they enter the detector. And then finally, above the detector, we have this little dome, which houses things like computing equipment, calibration devices, that sort of thing. Now you can see here, numbers are a bit small, but you could see this is an image, an artist's rendition of Hyper-Kamiokande. So the next generation detector we're currently building. And this is, you can see this is 68 meters in diameter, 71 meters deep. But maybe to give you a better sense of scale, I want to compare this to a building. So this is Tower Bridge in London, and you can see, if you cut off half a tower on the side, you can fit Tower Bridge into our detector. So that gives you a little bit of a sense of scale, of the scale we're talking about here. And we're building this detector deep underground, 650 meters underground inside a mountain. And this is going to be one of the biggest human-built underground caverns. So that takes obviously a lot of preparation. You can't just, grab a shovel and start digging. You need to do a lot of preparation work. So for example, you need to drill these boreholes to analyze the rock quality. And because these are boreholes, this is actually called a boring survey, which you can't see because of zoom medicine. Let's see if I can go more. Yeah. Oh. Okay. Sorry, that reminded the joke. So these are actually called boring surveys. And honestly, I had to listen to hours and hours of talks about those at our collaboration meetings. I agree. that name is appropriate. Then again, I'm not a geologist. Okay, but let's say we've done that. We figured out the rock quality. We know the best place to build our cavern. Yeah. It's not working. There we go. Okay, now we actually have to excavate our cavern. And you can see in the background, we're somewhere in the mountains in Japan, in a region with not too much, with a relatively low population density, not many big cities nearby. So you have to think about things like infrastructure. Obviously you need to get electricity, you need to get water to the building site. You also need to think about the local roads because they are pretty narrow. Are they big enough for these huge trucks to transport away the excavated rock? Or do you need to build some or extend some of the existing roads? And where do you store all of that excavated rock, by the way? Because as I said, that's a kind of 70-meter tall, 70-meter diameter cylinder. You can't just put that on the pile in your backyard. Forget about it. So you need to plan this really years in advance. And then, of course, if you dig too deep, there's awful stuff waiting down there. So you need a Bulwark early warning system. Also takes time and money. Okay, but let's say we've done all that. We've got the infrastructure. We've got our wise old wizard to get rid of any fire demons for us. And we've built the detector. And now we need to fill it. And to fill it, we use water, both because it's actually a pretty good detection material for neutrinos, but also because it's cheap and there's lots of it, so we can afford to build a detector that size. But even with water, we are at some point hitting limits of what's reasonable to do. And to fill Hyper-K, we need about as much water as 5,000 people use in a year. That's for drinking, taking a shower, washing their car, all of it. So getting all of that, if you're somewhere in the mountains, is really tricky. And you need to look for natural sources. You might be able to use the snow melt in the spring. But again, that's a lot of work to figure out. And then we're actually building a water purification system. Because we don't want some kind of natural water, even tap water, is not good enough for us, because even that contains some small trace amounts of radioactivity, low enough that we don't have to worry about drinking it, for example, but far too much for our detector because it's really sensitive. And this would completely overwhelm us. So we need to purify the water. And actually, if you have long hair like I do, or like my PhD supervisor here has, you need to be really careful. Because he was back in, I think, 2003, he was on a shift in the detector, like these guys here, doing some maintenance work. And then at the end of his shift, he laid back in the boat for a few minutes with some of his hair falling in the water. He didn't notice at the time, finished his shift, went home, went to bed, and then woke up in the middle of the night because his whole head was itching like mad. So what had happened? This ultra pure water here had sucked all of the nutrients from his hair, which then over the next couple of hours had sucked it from the rest of his hair and from his skin. So that's how pure this water is. And then, of course, all over the inside walls, we have these photosensors. And normally you'd say, oh, it's fine, I'll just run a cable from each of these to the top of the detector where I have my electronics and can read it out. Which works well enough if you have a small detector, but with a detector that size, some of the cables would need to be over 100 meters long, which means the quality of the signal really deteriorates. And also you'd literally have tons of cables in there, which would make the detector far too heavy. So you actually need, what we're going to do is actually put some electronics inside the water to use, to read out these photosensors there, and then only have a single cable that transports a signal from dozens of these photosensors. So that's, solves the weight problem and the cable length problem. But then you need these electronics to be watertight, to be low power enough that they don't boil your water. And you need to be, you need them to really work well and be reliable, because you can't shut down your detector, drain all the water and refill it every time you have to fix a problem with these electronics. So that makes your life a little harder. So again, none of these problems are unsolvable in principle. It's just, when you get into it and when you go beyond, oh, we're building this detector, and you look into what this actually means, there's lots and lots and lots of these tiny little problems that personally, before I started working on this, I never thought of. So that's kind of a glimpse behind the scenes of most of our day-to-day work. Most of it is not, fancy exploding stars. Most of it is this sort of thing. But anyway, so where are we right now? We got approved by the Japanese government a year and a half ago, and we're currently digging the tunnels towards where the cavern will be. The plan is to, finish the tunnels next year, dig the cavern for the next 2 years, and then build the detector and actually fill it and start data taking 5 or 6 years from now. And to do this, to work on an experiment of this size, that's not something that a handful of people can do on their own. So we've got this huge collaboration of about 450 people from 20 countries. Morocco just joined. So from 20 countries all over the world. And that's really great. It's good to have experts on so many different things all working together. The only really big pain in the ass is meeting times. So yeah, I've had meetings at 6 a.m. I've had meetings that go past midnight. It's a bit of a problem. But yeah. Okay, so that's our detector. That's what we're working on right now. And let's talk a little bit about the physics that we can study from that. Let's talk about supernova neutrinos. Now, first of all, what's a supernova? This is a supernova. So that's one single star that explodes at the end of its life and can shine almost as bright as this whole galaxy of billions of stars. And so the kind of astronomer's rule of thumb is this: however big you think supernovae are, you're wrong. They're bigger than that. And there was one very nice example for this, which I saw on a webcomic called XKCD, which I hope some of you know. It was this question: which of the following would be brighter in terms of energy delivered to your retina? Option 1, the supernova that's as far away as the sun is from Earth. Or option 2, a hydrogen bomb pressed against your eyeball. So what do you think? What's brighter? Yes, excellent. Yep, supernova is 1 billion times brighter. So yes, supernovae are pretty mind-blowing. And to me, that's really the fun thing about this job, right? I study some of the biggest explosions in the universe by using some of the tiniest ghost-like particles in the universe. So I have these two completely different scales, and yet they fit together perfectly. That to me is really what I love about this research. So supernovae are one of the biggest bangs since the original Big Bang. Their end products are neutron stars or black holes, which themselves are interesting astrophysical objects. And also this explosion can lead nearby gas clouds to collapse and to form new stars. So it's the circle of life, even for stars. And then there's one more very important role that supernovae play. Supernovae, shown here in green, form a lot of the chemical elements around you. So anything from the oxygen in your lungs, to the calcium in your bones, to the arsenic in your favorite Agatha Christie novel. So all of these elements are formed in supernovae, and life as we know it could not exist without them. And yet we don't really understand how they explode. And we've observed thousands of them. We observe one pretty much every night by now with optical telescopes. The problem is those can't actually tell us about how the supernova explodes, because you can only ever see, with optical telescopes, you can only ever see the surface of the star. You can't look deep inside the star where the explosion actually takes place. It's like, standing on the outside watching a building being demolished, and then trying to figure out, well, what explosive exactly was used. You can't do that by just looking from the outside. So luckily, supernovae produce a lot of neutrinos. And just a footnote for astronomers in the audience, I'm ignoring type 1a supernovae. Those are different, those work in a different way, barely produce any neutrinos, so let's leave them aside. So luckily, they produce a lot of neutrinos, so we can learn about what's going on inside. Now the problem with neutrinos, they're hard to detect, so we need a very nearby supernova so that we detect enough neutrinos that we can actually learn something. And so far, that's only happened once, back in 1987, famous supernova 1987A. And we saw about 24 neutrinos, half of them shown in yellow, in the original Kamiokande detector. And this is the energy of the neutrinos over the time. You can see it's about 10 or 12 seconds here, this burst. So that's all the data we have, right? Lots of neutrinos at the start, and then fewer and fewer neutrinos for about 10 seconds. That's all. And so from that, we can learn a little bit. We can figure out, okay, if we've detected this many neutrinos, how many were produced approximately? And then we can learn that those neutrinos produced make up about 99% of the total energy from the supernova. The kinetic energy of the explosion itself is about 1%, and the visible light, which again shines as bright as the whole galaxy of billions of stars, that visible light is just a fraction of a percent of the total energy released. Then we've learned that the neutrinos arrive a few hours before the visible signal. And I'll talk a bit about why that is in a few slides. And that's pretty much it. And I mean, we can do some things about figuring out the speed of these neutrinos, which give us a limit on their mass. And we can say, okay, well, if neutrinos were produced for about 10 seconds, that means we can't have produced too many other hypothetical particles that theorists make up, because otherwise those hypothetical particles would have transported away all the energy much more quickly, and there wouldn't be enough energy to produce neutrinos at the later times. So from all of that, from these 24 events, there have been over 1,600 papers written, so about 1 week for over 30 years, which tells you a little bit about how important this one discovery was. And actually, on the 30th anniversary of this, we had a little conference in Tokyo. And one evening we did a celebration. We went up into some restaurant on the 12th floor on some skyscraper, looking over the Tokyo skyline. All these neutrino people. There you have, this is actually now the spokesperson of Super-Kamiokande. He was a PhD student back then in the 80s, and he holds, I don't know if you can see it, he holds the original tape on which the data back then was stored. If you don't know what tape is, ask your parents. So they were celebrating, having speeches, and then at the end of the evening, we started singing "Happy Birthday" to the supernova, which, you know, happy birthday to you, happy birthday to you, happy birthday, dear Supernova 1987. Hey. It doesn't work, far too many syllables. We still did it. We had lots of fun. So that's all we know. Now here's what we think we know. And most of this comes from computer simulations, which, am I allowed to curse? Sure. Most of what we think we know comes from computer simulations, which are really fucking hard, okay? They're a really difficult problem because, you know, you've got all four fundamental forces play a role, right? Normally, generally in life, you care about gravity and everything else, like, you know, me hitting the wall, me holding this laser pointer, is just electromagnetic interactions between atoms in my hand and atoms in the laser pointer. So just gravity and electromagnetism. In particle physics, usually you don't care about gravity because these particles are so light, that all the other forces completely overwhelm that. But here we actually have to worry about all four forces: gravity, electromagnetism, and the strong and the weak nuclear force. We have to worry about nonlinear hydrodynamics because you've got the gas, the plasma, inside these stars flowing in really chaotic ways. All of this is highly relativistic because you've got obviously extreme masses. You've got this star collapsing at something like 10% the speed of light. And all of that at extreme temperatures, extreme densities, which are hard or in some cases completely impossible to reproduce on Earth in a lab. And even if you can reproduce them, it's at microscopic scales and not at the kind of hundreds of kilometer scales we're talking about inside the supernova. So that's really, really difficult. And around the time I started my PhD, there was this paper here by one of the leading groups doing these computer models, these computer simulations of supernovae. And they write that there is a long list of numerical challenges and code verification issues. Basically, we can't do it in as much detail as we want, so we have to use some approximations. We don't know how good they really are. And then they say results of different groups are too far apart to lend ultimate credibility to any one of them. So we've got all these simulations. We don't know how good they are. We don't know, which one is more true. So that's a problem. And actually, stars often don't even explode in these simulations. And we don't know whether that's just one of the approximations we use that's not working terribly well, whether that means we're missing some essential physics, like some other kind of particle that we don't know about yet, which changes the outcome. Or it could be that, maybe some stars don't actually explode in nature and they just collapse into a black hole. We don't know. So, any simulation results, should be taken with a grain of salt. That said, let's talk about results. And while we disagree on many of the details, the kind of basic picture seems to be reasonably well settled. So we start with a star that's about 8 or so solar masses, which consists mostly of hydrogen, and that's fusing into helium. That's what our sun is also doing right now. And then in a heavy enough star, this can go on, and it can fuse helium to things like carbon, oxygen, heavier and heavier elements, until you finally reach iron. And at that point, it stops because you can't gain any energy by fusing 2 iron nuclei together. So the iron just accretes in the core of the star, and then the death of the star begins. So when you reach about 1.5 solar masses of iron, this inner core will collapse under its own weight. And then I will show you with this ghost emoji, I will show you what the neutrinos are doing inside there. Right, and let's zoom in a little bit. So we've got this core collapsing, reaching 10% or so of the speed of light as it falls in, and the matter in the center gets denser and denser until you cannot compress it any further. And at that point, the infalling matter basically hits the wall and it is thrown back. So this collapse turns into an outgoing shock wave, and the neutrinos at the center, meanwhile, are stuck. Because neutrinos can go through a thumbnail, they can go through the whole Earth. But at that point, the matter in there is so dense that even neutrinos can't make it through. Even neutrinos get stuck. And so you've got this outgoing shock wave, and it uses up most of its energy to split the remaining iron into free protons and neutrons. And what happens then is these free protons capture all the remaining electrons, and you get this, they produce neutrons and neutrinos. So you get this sudden burst of neutrinos, and out there in the outer layers, neutrinos can escape. So you get this burst of neutrinos, and the shock wave has used up most of its energy for that. So it slows down, and then over the next, neutrinos in the center are still stuck, but over the next half a second or so, the vector falling in produces a steady flow of neutrinos, which then escape. And meanwhile, the neutrinos at the center, most of them still stuck, but the first ones, like when you imagine you're in a big crowd of people and you can't really make your way out, but over time you finally fight your way through. And that's what these neutrinos are doing. The first ones are finally making their way out of that crowd, and most of them will just leave the star, but a few of them will interact in this shockwave layer and deposit a little bit of energy. And because there are so many neutrinos trapped in here, that little bit of energy from a small fraction of those neutrinos is enough to give the shockwave a little kick to revive it, and then the star explodes. And over the next 10, 20 seconds or so, the neutrinos in the center are slowly all making their way outwards and escape. So in short, in one diagram that's very much not to scale, I should warn you. What you have is this initial peak as the first shockwave moves out and transforms all the matter into neutrons and neutrinos. The shockwave slows down, and then the next half a second or so, matter from the outside falls in, produces a steady flow of neutrinos. And if the shockwave sloshes around a bit, like pretty similar to the tea in your teacup, when you walk holding it, it sloshes a bit back and forth. It's pretty much the same hydrodynamics going on inside the sun. So if it sloshes back and forth, the amount of matter that falls in changes over time. And so you could get these kind of wiggles in the signal here. And then finally, the first neutrinos are starting to escape. They revive the shockwave, and the star actually explodes. And then over the next 10, 20 seconds, the remaining neutrinos escape. So that's the basic idea of what we think happens. And many of the details of how exactly these wiggles behave, how long it takes to revive the shockwave, all of that is hotly debated among the people running these simulations. But in Hyper-Kamiokande, instead of the 2,000 events we saw before, we'd expect something like tens of thousands or hundreds of thousands of events if we have a supernova in our Milky Way. And we would be able to reconstruct the time and the energy of each neutrino. So we can see kind of millisecond by millisecond what's going on in every single point in time. What's the temperature inside the supernova? What nuclear processes are going on, etc. So that's how we can learn about how the supernova actually explodes. And this was actually my PhD research, was using 5 of these different models. And I'm focusing here on this middle period, because that's the one where there are the most question marks. So I've got 5 different models here. You can see they all behave a little bit differently, predicted different numbers of events. Some have these wiggles, some don't. They predict slightly different energies. And I was looking at, can we actually tell them apart with Hyper-Kamiokande? And the answer is we do. So this is comparisons, pairwise comparisons of 2 models. For example, if this likelihood function we use here, if that has a positive value, so to the right of that purple line, it means it looks more like the black model labeled on the left. If it's to the left, it looks more like the red model on top. And you can see most of them are quite nicely separated. Just one or 2 of them, there's a little bit of overlap in the middle, but we're quite good at telling them apart. And this is if the supernova is anywhere in our Milky Way, or even just outside our Milky Way in the Large Magellanic Cloud, for example. So we can actually tell these models apart once the next supernova happens, once we detect it with Hyper-K. And then, meanwhile, because these supernovae don't happen very often, like maybe 1 or 2 times per century, so it's a long wait. But meanwhile, what we'll be looking for are these what are called supernova early neutrinos, where the idea is, okay, instead of one supernova that's very close, we have billions of supernovae that are very far away. And from every single one of them, we will only detect a tiny fraction of one neutrino on average. But the billions of times, billions of supernovae where you detect a billion of a neutrino each, still a handful of neutrinos. And those can't tell you about a specific supernova, of course. They can tell you kind of about the average supernova, or about how the supernova rate changes over time throughout the history of the universe. And actually, the first detection of these neutrinos, of these supernova early neutrinos, is probably going to be just a few years from now in Super-K. But they will only be seeing maybe 2 or 3 of them a year. So just about enough to detect them if you really eliminate all your backgrounds. But you can't do too much with that few events. So in Hyper-K, over its lifetime, we will detect probably hundreds of those. And that will let us study them in much more detail and figure out which of these different theoretical models is most accurate, for example. Okay, and in the final, I think, 5 or 10 minutes, I just want to talk about the Supernova Early Warning System, or SNEWS. And there's something really interesting happening in the last couple of years of astronomy, which is the advent of what's called multi-messenger astronomy. So you're not just using your telescope to look in the night sky, but you combine observations from telescopes and from gravitational wave detectors or from neutrino detectors. So you have very different ways of looking at the same object in the night sky, right? And these, we talk about how neutrinos can tell you very different things from what optical observations can tell you. So having these multiple different ways of looking at the same object is really interesting and tells you a lot more than just in one way. It's like you're not just seeing it, you're also hearing it. So you have multiple senses, and that's quite powerful. And for a supernova, what actually happens is you see these neutrinos immediately as the explosion happens, right? Because the explosion happens and neutrinos are produced and they escape the star with almost the speed of light. Meanwhile, this shock wave takes anywhere between minutes and many hours until it actually reaches the surface of the star. And only once it breaks through that surface, that's called the shock breakout, SDO, only then do you see an electromagnetic signal. So there's this long time delay, and the light doesn't catch up on the way to Earth. So neutrinos arrive earlier. And that lets us do something interesting. If the neutrinos arrive anywhere between a few minutes for these very compact, what's called Wolf-Rayet stars, to hours or a day or two for these larger stars. So if the neutrinos arrive before the light, we can actually use them as kind of an early warning system for astronomers. And this is really useful because these supernovae in our galaxy happen very rarely. once or twice per century. So it's really a once in a lifetime event. And we want to learn as much as possible when it happens. So any advance warning is really important. So what the basic idea of SNEWS is can we use these neutrino detectors as an early warning system? Like if we see something that looks like a supernova, not just in one detector, because that can always be some kind of, fluke, or it could be, maybe someone left a calibration source in there and forgot it. It happens. So if just one of them sees something, that could be a mistake. But if multiple neutrino detectors all around the world see something like a supernova at exactly the same time, that's worth shouting from the rooftops, right? And we want to tell astronomers about it. So the original SNEWS started about 20 years ago. It has been running completely automated mode for 15 years now. We've got 7 detectors participating, including Super-K, including also Ice Cube here at the South Pole, which is really cool. This cubic kilometer of ice, it's instrumented and acts as a neutrino detector. And really, ideally, what we want is what's called these 3 Ps, right? We want a prompt alert, ideally within a minute or so. We want to point the astronomers to where in the sky the supernova will be, which it currently can't do. So we'll leave that up to individual experiments. And we want to be positive it's a real supernova. And originally, 20 years ago, they set the false alarm rate to less than 1 a century, because we were worried about this boy cried wolf effect, where if we ever say, "Ooh, it's a supernova, everyone get excited, get your telescopes ready," and then it's a false alarm, we were worried that no astronomers are going to trust us ever again. So we want to be very certain. Now, in the Earth 20 years, a lot of things have happened. We've got a whole generation of new detectors, including Hyper-Kamiokande coming soon. And then this multi-messenger astronomy has really kicked off. So you had this gravitational wave event in 2017 from the binary neutron stars that collided, which we detect those gravitational waves and in lots of electromagnetic wavelength. We had, I think the year after that, this event where we saw neutrinos from I think a blazar that was flaring up. So basically a giant black hole in the center of the galaxy that was eating some matter. And we saw that with neutrinos and then with electromagnetic telescopes. And over the last few years, we have particle physicists and astronomers have started collaborating more closely. We now know each other better, we trust each other, so we don't have to worry about this boy who cried wolf effect anymore. And we can be more forthcoming about sharing when we think there might be a supernova, if we're not quite certain. And then we also have improved capabilities like some automated telescopes that can, within a few seconds, point at any direction in the sky. So if an alert comes up from gravitational wave detectors in the past, or hopefully from neutrino detectors soon, they can look there within seconds and try to find a counterpart. So from all of these developments, we started to work on what's called SNEWS 2.0. We published a paper last year, which is on the preprint server here. And that's been really redesigned for this new era. And just one thing I want to talk about before I finish here is about pointing. So far that's been left up to individual experiments because they can do it reasonably well, but it's also pretty slow, right? Because you have to detect these potentially thousands, tens of thousands of neutrinos You have to reconstruct them all. You have to run your advanced algorithms to figure out the direction from that. And that can take minutes. It can take, in the worst case, hours. We don't have that much time. We want, ideally, some rough direction as quickly as possible. So what can we do? Well, if we have multiple detectors all over the world, we can actually use triangulation between them. So if we see, for example, the first neutrinos arriving in Super-K in Japan, and then a few milliseconds later they arrive at a detector Europe, and then another few milliseconds later they arrive in Ice Cube on the South Pole, then we have a pretty good idea roughly where in the sky those neutrinos were coming from. It's not as accurate as doing a full analysis from a single detector. So you get about 10-degree uncertainty, which is about 20 times the size of a full moon. So you can't tell astronomers exactly, oh, it's going to be there. It's more of a well, somewhere in that direction over there. But that's still really helpful for figuring out which telescopes are best suited. And if the supernova is close enough, maybe you can even narrow down the list of candidate stars. And then we've got actually cooperations with, for example, the American Association of Variable Star Observers, which are looking at many of these candidate stars regularly over time to see how they change their brightness, their spectrum. So if we detect the supernova with these neutrino detectors, we'll send out an alert to them and ask these hundreds, potentially thousands of amateur astronomers all over the world to get their telescopes out to look through all of these candidate stars, see if any of them behave strangely, so that we have not just observations just after the supernova exploded, after the electromagnetic signal became visible, but also of the time period when it first became visible and just before. So we can extract as much knowledge as possible from this once-in-a-lifetime event. With that, I'm done. I will hope I convinced you that neutrino astronomy is this whole new window on the universe, which is quite different and complementary to electromagnetic astronomy. I talked about Hyper-Kamiokande, gave you a bit of a glimpse behind the scenes of what it's like to build such a huge detector, including some of the not so glorious parts. And then I talked about this SuperNova Early Warning System and how we're preparing to get the most of the next galactic supernova. So thank you very much. And I look forward to your questions.
Thank you, Dr. Jost, for the wonderful talk. Now we have about 15 minutes for Q&A. So if anyone in the audience would like to ask a question, please raise your hand and I'll point to you. We can also try to take a few questions from the online audience. So if anyone watching on Zoom has a question, you can put it in the chat. So would anyone in the audience like to ask a question? Yeah.
You said the Hyper-K is like about 8 times bigger than Super-K, but the numbers you gave for how many neutrinos it will likely detect was a lot more than 8 times, right?
What numbers specifically?
The supernovas, like the numbers you gave was like 12.
Sorry.
Oh yeah, that was that.
Sorry, I'm confusing myself.
Yeah.
There we go. That's a bit of an unfair comparison. So first of all, these 12 events in 1987, those were not in Super-K, but in the original Kamiokande. So that gives you a factor of 20. And then that supernova was not in the Milky Way, but in the Large Magellan Cloud, which is this dwarf galaxy just outside the Milky Way. That gives another, it's about a factor of 5 in distance. So because of the number grows as r squared, gives you a factor of 25 in the number of neutrinos. And this is for supernova somewhere in our Milky Way.
So it is in how big it is.
Yeah.
Right, with a question from the chat clarifying about the water in the Kamiokande. So what is in the super pure water that took out all the nutrients out of the guy's hair? Are there chemicals?
Well, there's nothing in there. and that's exactly the point. So normally in water, you have a little bit of different salts, the salt in the water. Here in this ultra pure water, you have none of that. So you have this basically difference in concentration between people's hair, people's skin or whatever, and the water. So it basically sucks all these nutrients out of the skin, out of the hair. It's just like if you had one room that's complete vacuum, one room that has air in it, and then you bring them into contact, the air will stream over.
Right. Any other questions in the audience? Thank you.
Is there a specific reason why Japan was chosen as the country? Because I would imagine that there are some earthquakes close by which could be problematic.
So the reason Japan was chosen is pretty much here. Right. So the original Kamiokande detector was small enough that just a handful of different universities could work together and build it. And so a few Japanese groups built this. There was another detector in the US called Irvine, Michigan, Brookhaven, after the 3 groups who built it. And then through, I guess, some accident of history, possibly because maybe there was politics around funding, maybe it was turned out that Kamiokande was a bit more successful on these low energy neutrinos like supernova neutrinos. They decided to build this next detector, Super-Kamiokande, and that was mainly paid for by the Japanese government. So they most of the people working on it were the same who had built the original Kamiokande detector. So they wanted to build it in the same place. And then same for Hyper-K. And so in terms of earthquakes, which you asked about, it's not too much of a problem here. So don't think I have a map of Japan anywhere. No. But in principle, these faults where you have most of the earthquakes are, I think, right at the coast of Japan, near Tokyo, for example. Whereas this detector is about 300 kilometers northwest of Tokyo. So it's reasonably far away from these, from the most dangerous areas. But yeah, absolutely, we've got geologists to take this into account, figure out the rock stability, figure out how we need to actually engineer the structure of this tank. So the structure holding up these photosensors, for example, so that it is stable enough to withstand an earthquake of a certain magnitude. So yeah, that's absolutely taken into account. Very good question. Thank you.
If I recall my cosmology lectures from a few years ago. Prior to the CMB, you get the emission of a sort of cosmic neutrino background. Are there any ever going to be prospects of detecting that, and how would you
So what I will say is that this cosmic neutrino background, yes, is absolutely a thing. We fully expect it to exist. We have not detected it yet, and it's also incredibly tricky because the cosmic microwave background has a temperature of about 2.7 Kelvin for various technical reasons, which you would probably know better than I do after that cosmology course. That cosmic neutrino background is a little lower energy still. And it's so to the point where those neutrinos, I think, aren't even relativistic. So they have, I don't know, millions and millions of times less energy than these supernova neutrinos we're detecting here. So certainly with these detectors, absolutely no chance. I think there are a few ideas of how, in principle, you would be able to detect neutrinos with that low energy, but I don't think it's anywhere close to becoming reality. Does that answer your question?
We have another question from the chat. Are scientists working towards taking the next step in observing or calculating the things that which cannot be seen in supernovae computer simulations?
So are we basically developing better and more accurate computer simulations? Yes, all the time. So there's probably, I don't know, a handful, maybe 10 or so different groups all over the world working on this. And there's different ways. So for example, one thing you can do, and there's, for example, a group in Garching near Munich, where I did my undergrad, which is following this approach. They're trying to make computer simulations that are as precise as possible, which means you need this giant supercomputer and you keep it busy for weeks or months on end just to run one single simulation of a star. And those are great. Those can tell you a lot. On the other end of the scale, you can have very simplified models where, for example, you assume they're spherically symmetric. Close enough. Saves you a lot of computing time. And you use a variety of different approximations to simplify some of the underlying physics. And then what you can do then is, instead of one incredibly accurate model, you can run hundreds and hundreds of not terribly accurate models, but you can run them, for example, with different progenitor masses, or you can use different rotation velocities of the progenitors. And then by running hundreds of these, you can compare, okay, how does one parameter like the initial mass, like the rotational velocity, like the chemical composition of the star, how does that affect the outcome? So you can do these kind of parametric studies. So yeah, there's lots of different approaches to develop these simulations further.
Right. We're just about out of time, so do we have one last question from the audience?
How often does the water have to be changed?
How often does the water have to be changed? Pretty much constantly. So we are constantly basically extracting old water from, I think, top of the detector, sending it through the purification process and refilling it from the bottom. And I think in Super-Kamiokande right now, the water is on average exchanged every couple of weeks, 1 or 2 months or so. Because yeah, you have some bacterial growth in there. You have, for example, radon gas from the surrounding rock slowly making its way in, stuff like that. Yeah.
All right, that's all the time we have tonight. Thank you everyone for coming. And thank you again to our speaker, Dr. Jost, for the wonderful talk. Right, before everyone leaves, I would just like to remind you that our membership officer, Ting Ting, is still taking membership signups at the back of the, sorry? Yeah, she's still taking membership signups at the back. So if you would like to sign up, you can do that here. Also, so if you've gotten memberships in the past month, there's a good chance that your membership card has been made. So you can look for Ting Ting as well to collect your card. And yeah, that's all for tonight. Thank you so much for coming, and we hope to see you again next week.